All right, so let's get started with the second part here. And if we go to the picture that we ended up with in the last part, it was this one, where we talked about the notion of taking a Boolean formula and compiling it to a circuit type. And depending on that type, then certain problems that are generally difficult become easy, assuming the compilation is successful. Now, we motivated this by looking at these particular problems because they're very special. They are prototypical of a whole set of complexity classes. The study that we're going to do next, where we will look at a whole bunch of circuit types, will be done in a little bit broader or maybe more detailed setup, which looks like this. We do have these circuits, which, as we mentioned, are based on negation normal form circuits. And then we have some properties, and now I'm showing you the names of some, decomposability, determinism, and so on. If we put these properties or some of combinations of them on these NNF circuits, we get circuit types that have specific properties. But typically, people study these from 2 points. One of these points is what kind of operations or queries that are generally hard, which become easy when you apply to these circuit types. You're familiar with many of these: consistency, validity, and so on. Some of them we'll have to explain. And there's another set here that we call transformations. So these circuit types are studied from the point of view of what operations become polytime on a particular circuit type. And that is the tractability part. How tractable are these circuits? You'll see that some of them allow this to be done and that, but not this, and so on. The other angle where people study these circuit types is what people call succinctness, which is effectively the size of these circuits. Because what you'll see is as you add more and more properties to these circuits, they become more powerful in the sense that they allow more things to be done in polytime, but that comes at the expense of these circuit sizes growing larger. So there is an interest there in talking about how do they compare in terms of size. And we will say, for example, that one circuit type is more succinct than another, meaning we expect it to be smaller, or less succinct, we expect it to be larger. And that study of tractable circuits from these three dimensions of properties and polytime operations and succinctness, is done in AI under the label of the Knowledge Compilation Map. Now, what is the term map comes from? You'll see that in a little bit. So what we will do next is show you some kind of a map of these tractable circuits. It will be in some parts very specific, and in some parts we'll just walk through things, because I just want you to see the big picture of what's going on here. And after we finish this part, which will have to probably flow into the next lecture, then we will take a subset, a select set of these circuits that have been quite influential, and we'll zoom into them. So we will be revisiting some of these concepts again, and we will be focusing on the ones that we will be using in applications later. So just first, a couple of words on what's going on here before we keep going on. So that set is broken into two things: queries and transformations. Queries are questions you ask about a circuit. You do not modify the circuit. You know some of these. Consistency, that's satisfiability. I give you a circuit and ask, is it satisfiable? Is there an input to that circuit that will generate an output of 1? You know validity as well. You know entailment. Now, you'll see there are 3 types of entailment. So if you have delta 1, does it entail delta 2? That is entailment. And if we're talking about a circuit type, let's say a circuit type called OBDD, one of the famous ones, then this sentential entailment is saying, can you test whether one OBDD implies another, right? So we have an OBDD here and an OBDD there. That's the general test. Sometimes this is difficult. So we look at 2 variations on entailment. One in which we put a clause here. So we're not putting an arbitrary circuit. We're saying whether a circuit implies a clause that ends up being causal entailment. It's a simpler version of the general entailment test. And this guy here is, I will put here a term instead of a circuit. So I'm asking, does a term imply a circuit? And that's this guy here. All right, so the reason is, again, sometimes this is hard, but these are easy. You know about equivalence testing, whether two things are equivalent, and model counting you know about, and model enumeration, whether I can enumerate the models. The other set that people look at is what they call transformations, and this is when I'm actually modifying circuits. So I may take a circuit, delta, and I want to existentially quantify the variable x. That would be another circuit that is different from the original one. And then people are interested, can I do existential quantification or universal quantification in polytime on a particular circuit? And similarly for conditioning conjoin. So this would be, can I take two circuits and conjoin them to obtain another circuit? Now, one thing here that you have to be realize that now you can say, well, why is that hard? Just take the two circuits and put an AND between them. Well, no, I want the result to be also of the same type. So it may not be easy to actually ensure that the output is actually of the same circuit type and so on. Negate, can I take a circuit type and negate it? If you give me an OBDD, can I negate that in polytime and give you an OBDD back, and so on. So what we'll do next is we're gonna see how we can induce a whole taxonomy of circuit types through a very simple process of starting with negation normal form and then adding properties on negation normal form. And what I'll show you is pictorially what happens to these guys, to these set of queries as far as which one become tractable under what property. Now, you're going to see quite a bit of information coming through next. You not have to remember this. Some things you will have to remember and they'll become clear when we start zooming in, and I'll let you know what you need to remember. But some things we have to mention because you need to know that they exist in case you want to look them up later. So if you feel there's a lot of information coming in, don't worry. All right, we're doing big picture for now. And we'll basically tell you later what to expect, especially if you're worried about exams and so on. Okay, so we talked about this negation normal form circuits as being the basis of everything. We showed this picture because people are familiar with gates and so on. But in most of what we'll do, we will not look at pictures like this, but instead we look at these circuits like that. So instead of drawing an inverter or drawing an AND gate or an OR gate, we're just going to do this. All right. So this is a negation normal form circuits. Here are the inputs. And as you can see, these inputs are either variables or they're negations. So you can think of this variable B as being inverted before it goes through here. And these are the ANDs and the ORs. And as you can see, we can have multiple layers there. Now, there's no restriction on the number of inputs for a gate. So in this case, it's 2, but it could have been more. And in fact, everything here is binary inputs, but it doesn't have to be. So it's you can think of this as a rooted DAG. This is the root, and these are the leaves, and so on. Okay, this is the picture we're going to be looking at. Now, as I mentioned, what we'll be doing is we'll be looking at properties that we can put on these circuits. And this is the list we're going to go over today. There is more properties. What happened here is the story I'm going to show you is the original story that was told about the knowledge compilation map from a while back. And over the years, the map has been extended quite considerably, but we're still going to focus on the very original core. And at the end, I'm going to tell you about something that came up, which was major in terms of circuit types. But we're sticking to the very original story because it's sufficient to really give you the gist of what's going on, which is what we really need to do here. So what we're going to do is the following. We're going to walk through these properties. I'm going to explain them to you. And as we introduce each, we're going to see what is the impact on operations. All right, think of this now as an overview. We're going to revisit each one of these in the next couple of weeks, or highlights of these. Okay, we're going to start with the property of decomposability. This is the very first one. And this is a property that applies to AND gates in an NNF circuit. And it's very simple, actually. If you look at this AND gate and you look at the subcircuits that are feeding into that AND gate, what do you see? You see this guy here and that guy there. Okay, they're highlighted with different colors. Now, if you look at the variables that appear in this subcircuit, you're going to find that they're AB. If you look at the variables that appear in this subcircuit here, you find that they're CD. So what's the relation here? They do not overlap, all right? So the two subcircuits that are feeding into the AND gate are over disjoint variables. And this applies to every AND gate in the circuit. So if you check this AND gate here, you will see that one is over A, the other is over B. If you check this guy here, you're going to find that these guys are over AB, and you find these guys are over CD, and so on. So that is what is decomposability. Very simple property. If you have decomposability, the circuits are known as d-NNF circuits. And guess what? And we'll see this next. Satisfiability becomes easy on these circuits. If your circuit is decomposable, you can check satisfiability in linear time. You don't need DPLL or any of that. But of course, the trick here is how do you take your Boolean formula and compile it into a circuit that is decomposable. But if it is decomposable, you're done. You basically figured out the class NP. And the way we're going to be showing this, and that's what we'll be going through next, is we're building this taxonomy. So we had the original NNF, and that was not interesting in a sense that I'm going to mention now. And we added decomposability, and then we got a subset of this guy, and that's d-NNF, decomposable negation normal form. And if you look at the queries that I mentioned earlier, there were 8 of them. And you realize that 3 of them become easy on this guy, that is satisfiability, closure entailment, and model enumeration. So we're going to be building this because what's going to happen is the set of properties that we selected here will kind of lead to families of circuits with different kind of characteristics. So we'll move further, and you will see that some of these boxes have the blue color and some do not. And the reason here is you will get a blue color if you're at least able to do closure entailment in linear time. When this original knowledge compilation map was built, the idea that we will refer to a circuit type as being tractable if it at least can do closure entailment. Now you're going to say, why that? Why not satisfiability? The idea is satisfiability is only one query. So you may not want to just compile just to do one query, but closure entailment, there are so many queries. So that's a more interesting definition of tractability. So as we build this, you're going to see boxes being added that are white and ones that are blue. And that is basically the reason. So let's move on and do another property, which is known as determinism. Determinism refers to OR gates. So if you look at this OR gate here, and you look at the 2 subcircuits that feed into it, look at the first subcircuit. What does it represent? It represents not A and B. And if you look at the other subcircuit, and you will find that this is A and not B, right? So if we call this alpha and we call this beta, what's the relationship between alpha and beta? They're mutually exclusive, all right? And that's what we need in this property. If you take an OR gate and you look at any 2 inputs, they should be mutually exclusive. What this also means is regardless of how you evaluate the circuit, you will never have one on both of these wires, right? It's pretty simple. And this has to apply to every OR gate in the circuit. So we have how many OR gates here? We have this, and that, 5 of them. You can check them. And you will find that for each one of these, the inputs are mutually exclusive. All right. Again, a simple property, and you'll see when you put this with decomposability, major things happen. Let me add one more property here, and that is called smoothness. And in smoothness, it's also a property that applies to OR gates. And the idea here is that if you look at the input here and you see what are the variables that are mentioned, that is A, B. And if you look at the other input, what are the variables that are mentioned, that is A, B as well, they should be the same. And that's basically what I want from smoothness. It applies to OR gates, and it says every input to an OR gate should mention the exact same set of variables. Now, decomposability and determinism are big properties. They lead to quite a bit. You'll see that in just a little bit in terms of tractability, and they're hard to enforce. Smoothness is a different story. Smoothness is easy to enforce. In the worst case, in quadratic time, it actually ends up being a convenient property that makes the algorithms we're going to look at very nice. In fact, the nice thing about this theory is when we get to algorithms for how do you do this or that on these tractable circuits, you're going to see that they're very simple. They're all like one-pass algorithms. They just walk through the circuit, do something local at each gate, and you're done. So it's very elegant, as you will see later. Okay, so now we have decomposability, determinism, and smoothness. Let's see what happens to this map that we're building here. Okay, and now you're going to start to see a lot of information. And again, don't worry, we're just getting a feel of what's going on here. So look what happened. I had negation normal form. When I added determinism, nothing happened. It's still white. It's still not tractable. I didn't get anything interesting here. When I added smoothness alone, again, nothing happened. It's still white. Now remember, decomposability was pretty influential. When I added decomposability, I got satisfiability, closure entailment, model enumeration, all can be done now in polytime. So what do you do in this case? What happens if I marry decomposability and determinism, right? That is, I have a circuit type that satisfies both properties. Then I get this circuit type, deterministic decomposable negation normal form, right? So this is the child of these two guys. Look what happened here. Now, since this is a subset of this, all of these queries that were polytime on this should be polytime on that. So that gets these three. But on addition, I got three more, right? And probably the most important of these is counting. Now I can count the models of these circuits just because they're decomposable and deterministic in polytime. I can do validity, Now, what does this mean? This means this is an open question. We don't know if we can check the equivalence of two circuits of that type in polytime. And if you remember, we had 8 of these properties that we were looking at. So this is 1, 2, 3, 4, 5, 6, and 7, and there's one that is left. Okay, I don't know if anybody can remember what that 8 one that is missing. There's one that cannot be done, even with these two properties. So again, there's 8 of them. We can do 6. One, it's an open question, and one of these we can't do that. And what we have, the one that is missing is sentential entailment. Thank you. Someone already mentioned this. Sentential entailment is, again, I'm not expecting you to remember that, but just want to give you a sense. Someone is asking about the difference between model counting and model enumeration. Model counting gives me back a number. So you come and tell me there's 3 million models, number. Model enumeration, you print them. You start printing them, all right? Now, when we say polynomial, an output polynomial. So let's get to that subtlety later. I know people typically find that a bit confusing, but it will become clearer later. Now, look what happened here. When we married this with that, so we got something that is both smooth, deterministic, and decomposable. Nothing happened. We didn't get much. And I already alluded to this. The reason smoothness is useful because algorithms on this guy are nicer than algorithms on that, but they're as efficient from complexity point of view as far as being polynomial. Okay, this is one family of circuits that is based on these properties of decomposability and determinism. Now, when we finish this picture, we're going to see 2 other families pop up, one on this side and one on that side. And both of these families are driven by some major property and refinements on it. So in a sense, when we finish this, you're going to find really 3 clusters of circuits, and they correspond also to what happened historically, all right? You're going to find that the guys that we're building here have been around for a very long time and studied within computer science and AI. The guys that we're going to build on this side, they're also been around for a very long time, again, by computer science, more broadly, and maybe electrical engineer, and later by AI folks. These guys are the more recent ones, actually, the ones that we just started. And let's go and build the next two guys. And you will see that you're familiar with them in some fashion. And then we will finish this knowledge compilation map, or at least the very early version of it, before we go and zoom in on some of these guys. So the next property that leads to a whole new family is flatness. And flatness basically says that I only have two levels. So one and another. So these are basically flat circuits or shallow circuits, as opposed to nested or deep. And those correspond to things that you're familiar with. The nice thing about these flat circuits is you can write them as a sentence, right? So this guy can be written like this. You know what this is, right? What is that? What does this correspond to, this circuit type? Look at what's going on here. We had a form for this. d-NNF, exactly. Now, these flat circuits lead to d-NFs and c-NFs and subsets of them. So if I have a flat, okay, you get to see what's going on. And now there is a property called simple conjunction. So what is simple conjunction? Simple conjunction says I need to have an and an or after that. And the children of the and are over distinct variables. All right, so this is x, y, z. I don't want to have something like x and not x. So the children must be distinct, right? So this particular simple conjunction property makes sure that you're going to get a d-NF, right? So this is basically d-NF. And you'll see on the next slide how you get c-NF. But let me ask you a question. This is flat and satisfies the simple conjunction, meaning simple conjunction, just a conjunction of distinct literals. This circuit type satisfies a property that we talked about earlier. What is it? Remember, what I'm saying is the simple conjunction property is that every and is simply the children are distinct literals. You can't have arbitrary sentences with distinct literals. Think about it. We had decomposability, we have determinism, and we had smoothness. One of these. Which one are satisfied by this? Okay, someone's saying decomposability. Exactly. Because distinct literals. So there are no variables that are being shared. So if you look at any two children of the and, they do not share variables. So this d-NF is actually a subset of decomposable negation normal form. Now you see what's interesting there. So the simple conjunction property implies decomposability. Now, let's look at the one which you're expecting next, simple disjunction. Simple disjunction says I have an or then an and I want the children of the or to be, again, distinct literals, and this is c-NF. Okay, now let's see what happens with these two guys. If you look at the map now, we just added flatness. So we took NNF and added flatness, nothing happened. So this didn't give you much. Now, when we put the simple disjunction, we got a c-NF, nothing happened. It's still white. It's still white. But when I added the simple conjunction, I got d-NF. Now, remember, this guy is a subset of that. So it already inherits these three properties. So these three properties are all easy on this guy as well. But I didn't get any more. So you can think of this as the flat version of that. This is the deep circuit that satisfies decomposability because I don't restrict the level of number of layers. This is the flat version. According to the 8 properties we looked at, they look the same in terms of what they allow us to do in polytime. And guess what? Remember when we started, we talked about succinctness, like how large can things get? Well, this is strictly less succinct than that, meaning there are Boolean formulas that will blow up if you try to represent them as a d-NF, but they can be represented efficiently as a d-NNF. The extra nesting helps here. So shallow, deep, and for these 8 queries doesn't make a difference, but it does make a difference in terms of the size of the circuits. Okay, now I need to add 2 more here, and we will get to one of these in detail later because it plays a big role in explainability now. Again, we're giving a feel here of things. And we'll look at some of these more carefully. So we'll finish this story here, and then we go to build that story there. So the subset we're going to look at of this is known as prime implicate representation. Let's look at it again. Once more, assurance. Don't feel overwhelmed with what's going on here. So we're talking about a subset of CNF that satisfy these two properties. Okay, the first property says, in the CNF, I don't want any clause to subsume another, which means I don't want redundant clauses. What this means is you cannot have A or not B, and then also have A or not B or C. The reason is this is redundant. Given that this guy says either this or that, this guy either this or this or that, this is implied by this. So in this case, this is called subsumed, and I don't want it to be there. That's what's going on with the first guy. The second guy is best to explain by an example. Here's the CNF, and this says if some clause is implied by the CNF, it must be implied by a clause in the CNF. If you look at this guy, one of the clauses that is implied by it is the following: not A or C. This is actually implied by this guy, follows from it. And this guy says to satisfy this property, it must be implied by some clause here. That means you should be able to find one of these clauses that is a subset of this. So I don't need to look at the whole thing to check that this is implied. I need to just look at individual clauses, and that's not the case here, right? So you can think of this second property as some kind of a deductive closure. And if you have these two properties, then I want to say that this CNF satisfies the prime implicates property, and then we will refer to it as a PI representation. Here's a version of this where I added more clauses. I added 3 more clauses, and now this guy satisfies these two properties, right? This satisfied the first property. So both of these satisfy the first property. This guy does not satisfy this property, but this guy does. It's not as easy to check, but I will make a claim. Any clause that's implied by this guy is already either sitting in one of these 6 or is a superset of one of these 6. So in a sense, this CNF is kind of claused under logical deduction. If you want to do causal entailment, you don't need to do any hard work. So if I tell you, here's a clause, is it implied by this? All you need to do is walk through these 6 and check one by one whether any of them implies the clause. If yes, then yes. If no, then the CNF cannot imply that clause. This is a very special type of CNF. And you can get it easily using resolution, which you guys are familiar with. And in resolution, okay, I keep having this problem where I cannot put, okay, bear with me here. I'll try to avoid this in the future. Remember what resolution is. You take 2 clauses like this and you basically resolve over X and you get that. So if you take this CNF and just keep applying resolution as much as you can, you're gonna get this. And this will end up satisfying these 2 properties. You just want to make sure that you do not keep any subsumed or redundant clauses. And that's what's known as the prime implicate representation. There is a dual one for d-NNF. I'm just going to show you the slide, but we're not going to go over it because that dual one, which is called prime implicant. So there is prime implicate, which is a clause that is entailed, and there is a prime implicate on d-NNF. The reason I want to skip it now because this guy plays a major role in explanations, and we're going to study it later. You're going to be very comfortable with it. And this is where when you're trying to explain the decisions made by classifiers. So let's say you have a random forest or a Bayesian network classifier, and let's say it's meant to admit people to some program or give loans. And then you say, here's the customer, what do you say? And then the machine learning system or classifier says decline. And then you say, why did you decline that person? And you want to find an explanation that led the classifier to actually decline. You'll find that actually prime implicants play a major role. Prime implicants have been studying for decades in AI and computer science, but over the last couple of years, they come to the center stage as far as doing explanations and related queries. So we're going to get to them later. But let's see what happens to the knowledge compilation map. Again, we're doing an overview here. Here are the two guys we added. This is the subset of CNF, which is, they satisfy these additional properties. And this is the subset of DNF, which satisfy these additional properties. The additional properties, again, roughly no redundancy, and I need some kind of deductive closure. What happened here? Look, this guy was nothing. And then suddenly, how many I'm getting? 1, 2, 3, 4, 5, 6, 7. 7 out of 8 because of that additional property of effectively deductive closure. And look at what happened in this particular case here. I had d-NNF. d-NNF didn't give me anything. It just inherited 3 of these from decomposability. And now that I added this property, what did I get? 1, 2, 3, 4. In fact, if you add these guys to those guys, you get 7, and they're exactly these 7. And you can see why these two types of representations, prime implicants and prime implicants, they received a lot of attention in computer science and AI over the years. But their role somewhat diminished when these guys came up, and because of what we're going to put in there, in some applications, but then resurfaced recently in a new set of applications. Now, to get a sense of what kind of applications they end up not being influential, you have to look at what is missing from these 7, right? So we had 8 queries, correct? And what this is showing is that both of them satisfy 7. There is 1 missing from each. For those who remember these things, do you know which one is missing? Okay, someone said no counting. No counting. You can do a lot with these guys, but you cannot count. Now, why is counting is problematic, not being able to do counting? What things do you miss by not being able to count? Someone saying mash sat. Let's talk about applications. The class PP, what is that? When you're able to count, what can you do? Probabilistic reasoning, all right? So these guys don't help you with probabilistic reasoning and therefore quite a bit of machine learning. So that's why the role basically was not as influential because in those kind of applications, they can't help you there. And these guys allow you to count. This particular guy is very influential in probabilistic reasoning because it allows you to count. And that's start to give you the feel of this, knowledge compilation map. There's one more property we're going to introduce that ends up giving you a family here, which some of you will be familiar with. So someone is saying, can't you count by totaling the number of outputs from model enumeration? Well, again, here's the problem. If you have a billion models and you enumerate them, you have to do work linear in billion, right? But this is if you're enumerating them. So you're going to have to be proportional to the number of them. But model counting is independent of that. So when you're doing model counting, even though you have an exponential number of models, you don't have to do exponential work, okay? All right, let's do the last property, which will end up give us a few others, and you'll see a very influential circuit type that's gonna come up, and it relates to something that you've seen in other forms. This property is called the decision property. And what this property says is very simple. When you build your circuits, you build them this way. You build them using these fragments. Let's look at this fragment. You've got an OR, and look, you have 2 branches under it. X and alpha, not X and beta. Now, X is a variable. So this is a positive literal, and this is a negative literal. And alpha and beta can be built recursively using the same process. So this fragment, we call it a decision node, because think about it. We're trying to decide, is it alpha or beta based on the state of X, right? So it's making a decision. And let's look at the circuit that's built this way, okay? And now you're gonna see an interesting surprise, all right? So prepare. Here's a circuit that is built that way, and I've color-coded the fragments that correspond to decision nodes. So look what's going on here. Or now I have X1 and da, not X1 and da. So this fragment here is one decision node. Okay, and the boundary cases are either true or false. So now a decision node. You keep doing this, eventually you end up with true or false. Count how many decision nodes here. Someone type a number. In this circuit, how many decision nodes? I mean, the coloring should help you. Someone is saying 5. This is 1. This is another. 3, 4, 5. Excellent. We indeed have 5 decision nodes. Now, you probably know this guy, all right? If we adjust for notation, so look what I'm going to do next. I'm going to do a notational adjustment, and suddenly this circuit type is going to look like something you've seen and may have even played with. What is the notational convention? The notational convention is this. Instead of drawing the fragment this way, I'm going to draw it like this. I'm going to put a node with the variable x, and I say if x is true, go this way to alpha. If x is false, go this way to beta. Okay? Stare at this for a second. All right. Now, what we're going to do is, now we're going to go to this guy and do the notational substitution for each fragment and see what we get. Actually, I want someone to type. Do you know what we're going to get? When I go ahead and do the substitution for notation on the previous guy, you're going to get a creature that some of you may have seen. Someone is saying a decision tree. It's actually almost, you're going to get a decision graph. And I'll tell you what the difference between a decision tree and decision graph is. But here's what happened here. If you look at the circuit type, we do the substitution, you get this. And the difference between a decision graph and a decision tree is, in a decision graph, nodes can have multiple parents. So it's possible that you get to this node x3 by going down this path or going down that path. That cannot happen in decision trees. And so it's basically very similar representation, but this is more general. And here's something you should know. The fact that you can have multiple parents per node can lead to exponential reduction in size. So decision graphs are generally more succinct, strictly more succinct than decision trees. And we're going to get back to them later because this is a very important class of circuits, as you know. In fact, we will be looking at compiling certain type of machine learning classifiers into these representations. Now, there was someone who's writing and saying, are these circuits always deterministic? Now, again, we're not done with the story on these guys, but let me go back and let me ask the question. This, what of you posed? Are these circuits deterministic? What do you guys think? Are they? Remember, what is deterministic? Deterministic, if you go to every OR node, any pair of children should be mutually exclusive. In these circuits, there's always 2 children. This OR has these 2 children. This OR has those 2 children. Question, are these 2 children guaranteed to be mutually exclusive? Yes or no? Well, remember, someone is saying no. If we go back to this picture, here's the 2 children. Is this always guaranteed to be mutually exclusive with that? Someone is saying yes, because look, this is what? X and alpha. This is what? Not X and beta. Of course they conflict. One of them has X in it and the other has not X. So they are mutually exclusive indeed. And as someone observed or asked the question, yes, the decision property implies determinism. All right, so these are deterministic. Now, but interestingly enough, so far we don't get much. Okay, what happened? White guy, right, not blue. This is the subset of deterministic negation normal form. That is a special type of property called decision. It is deterministic, but I didn't get any interesting stuff. Now, if you want to get interesting stuff, what you should do? Now, look, I mean, what is this map here? It's a breeding map. We're basically sometimes taking 2 guys and marrying them and having an offspring. If you want to marry BDD with something so that you get something that is interesting as far as tractability, what do you think we should marry it with? Give me a property that we need to add maybe on these guys, and then they'll become interesting. What's one of the simplest properties that immediately gave us something? We started with that. Okay, let me run down. We have decomposability, we had determinism, we had smoothness, we had flatness. In fact, none of these gave us something on its own except for decomposability, right? Someone is writing decomposability. Well, let's see what happens if we put decomposability on top of these guys. What do we get? And what does it mean to be decomposable? Decomposable, remember, for AND gates, no sharing of variables. Okay, so what does that mean? You look here, I have x1. X1 cannot appear below. If you look here, I have x1, x1 cannot appear below. Okay, let's take this guy here. I have x2, that means x2 cannot appear below. That's decomposability. Now, if you look at this notational convention, decomposability has actually a nice way to phrase it. And that ends up being what? If I want to phrase decomposability on this, I know. I say an AND gate, if you look at any sub-circuits feeding into it, they cannot share variables. In these circuit types, AND gates always have one input being a literal and the other being something more general. But if I want to phrase that property on this, what should it look like? It's actually pretty nice. It's called the test one property. It says if you go from any path from the root to a child, to a leaf, sorry, from the root to a leaf, any path, a variable can only appear once. And this is known as the test one property. See what's going on? If you phrase it here, you say any path from the root to a leaf, a variable can only appear once on that. If you look at that same property on this figure, that's decomposability. In fact, people in computer theory have identified this property called test one. And when you put the test one property on a decision graph, you get what people call FBDDs, free binary decision diagrams. That's a circuit type, FBDDs. So FBDDs are BDDs with the test one property. That's one way to look at it. Or BDDs with decomposability, the same thing. And guess what happens? Well, let's build this up. Here's FBDDs. So they are a subset of this guy, and now a subset of this as well, because they are both deterministic and decomposable. And they still give you the same power as this guy, though. They inherit these 6. They still, equivalence has been open on them for a few decades, this question. And we still cannot do sentential entailment. By the way, this notion of we cannot do is all under complexity assumption that P is not equal to NP, but we're skipping those here. Now we have one more thing to do here. Someone is asking what happened here. Let me see. Okay, someone is asking about mods. Let me get to this at the end. I don't know how it popped up here. I should have mentioned it. Well, let me say, mods is simply the representation where you take a disjunction of all models of the Boolean formula. Okay, it's a bad representation, right? It's like a d-NNF, but every term in the d-NNF is an actual model. Okay, that's a very powerful representation. You get all 8 queries, but it's pretty bad because it's very not compact, right? You're listing all the models. But there's one more addition here, which is very, very famous and influential. And we'll get to it, and we're basically pretty much done with this knowledge compilation map overview. And that is, if we go back to this representation of decision graphs, we added the property of test ones. Test one says that if I go from any root to a leaf, a variable can only appear once. So I cannot test the variable more than once. But it leaves open the possibility of having different variable orderings across different paths. So it's possible in an FBDD to go down this path and have x1, x2, x3, but then go down another path and have x3, x2, x1. That's okay. We get our last circuit type here for today by saying, no, I want the variables to be tested in the same order across all paths. So regardless of how you go from the root to the bottom, you have to encounter variables in the same order. If you have that, you get something known as ordered binary decision diagrams, or OBDDs. And let's see what happened here to get OBDDs. OBDDs are negation normal forms with decision property, decomposability, and ordering. This is not how OBDDs are typically discussed. People discussed OBDDs, introduced them, and studied them extensively before this knowledge compilation map. They were not presented as subsets of NNFs and as part of this theory that I'm showing you here. And sometimes people will tell you this, just to give you a sense of how important OBDDs are. They will tell you this is perhaps the most studied representation of Boolean functions or tractable Boolean functions. There is significant literature on this kind of representation. It's pretty intuitive, as you can see. And part of the reason why it got this attention as well is if you add it to the knowledge compilation map, look what happens. Here it is, a subset of FBDDs. And what happened here? How many queries did I have that we were looking at? 8 of them. All right. This guy can do them all in polynomial time, including counting. So it's pretty potent. It's pretty powerful in terms of how much power you get if you're able to compile your Boolean formula into an OBDD. Now, you may say, but wow, 8 of them, everything? This beats everything that we've seen here, pretty much except for mods. Then you would say, why don't you always use that? Why do you care about the other stuff? So can someone tell me, why can't we just like go home and say, oh, OBDDs, let's not worry about any other thing and kill all of this material? Okay, someone says succinctness. Exactly, because these tend to be bigger than others. And as a result, you may not succeed in compiling your Boolean formula to an OBDD. And if you don't need the power that OBDD gives you, if you're just happy with counting, for example, then you may go and compile into this guy instead, which is actually more succinct. So the succinctness is important. Okay, guys, let me wrap up here with a few words. First, this is the original knowledge compilation map from about 2 decades ago. A lot has happened since then, but we're doing here the original one because it really gives you the whole gist of it. And there have been developments and new circuit types. And there's one particular influential one, which we will talk about because it plays a big role, especially in learning from data and knowledge. And that is known as SDD circuits. So I introduced these, this was 2011, I believe. It's not here. And we're going to look at it later. And by the way, these decomposability, determinism, and this family is all actually from my group over the last 20 years. And there is another type of circuit types called structured decomposability. We're going to get to this later. So again, this is the very original knowledge compilation map. I hope you see what's going on. As far as succinctness, let me show you this picture. We're not saying much here, except that if you focus on these 4 guys, decomposable, deterministic, FBDD, OBDD, what happens is as you go down, you're adding more properties, right? So we started with decomposability, then we added determinism, then we added decision, then we added ordering. This guy has all of these guys. What happens? 2 things happen. As you add more properties, first, you get to do more, right? So here with this alone, you can do diagnosis and something called non-monotonic reasoning. You add determinism, you can start doing probabilistic reasoning. You go down, you do more and more. But also succinctness suffers. So things get bigger, right? So they get bigger. And this notion of bigger is not just an informal one. There is a formal definition of succinctness. And people typically talk about what they call separating functions, that is, or separating formulas. So there is a class of formulas that I know can be represented as a d-NNF efficiently, but will blow up if I try to do it using this guy. Similarly, if you have a function or a Boolean formula that I can represent, usually it's a class of Boolean formulas that I can represent efficiently using this guy, but it will blow up if I try to use an OBDD. That's called a separating function. And people have been, particularly in computer theory, identifying these separating functions. And these are some of the well-known ones. There's something called the hidden weighted bit function, which separates OBDDs from FBDDs, meaning it can be represented efficiently using an FBDD, but will blow up using an OBDD. The odd parity function can be represented efficiently using d-NNF, but will blow up if you do a d-NF, and so on, okay? But that's basically the picture. So if we go back to this, here, what's known as a knowledge compilation map, what we will be doing starting our next lecture is we will zoom in on a few of these that have been very influential. And now we've been making these claims about, oh, you can do this in polytime and in polytime. You'll see how much fun it is, in fact, to both see why does decomposability allow you to do SAT in linear time? Why does decomposability and determinism allow you to count? In fact, you'll be able to discover these. They're pretty intuitive. And the even more fun is when you see how simple the algorithms are on these tractable circuits to compute these queries. It's just a fantastic theory. And then when we focus on few of these, we're going to look at knowledge compilers, because everything is now reduced to simply taking a Boolean formula and getting a circuit of the appropriate type. You know how to do this, you own a lot of things. We'll talk about that. And that would be basically our second part of the foundations. And when we talk about knowledge compilers, you'll see all of the techniques we did in the first part will become relevant. Folks, that's it for today. Thank you very much. And I will see you on Tuesday. Thank you.